Okay, kids, let's talk about vectors and vector notation. Cute joke too, right? Okay, so just a reminder that vectors are a type of measurement that have both size or magnitude and direction. That's different than a scalar quantity, which only has a size or magnitude. This chapter is going to talk and focus mostly on addition and subtraction of vectors and different methods to do that. Let's just get through some different ways you might see vector notation, meaning how do we represent a vector. Well, your textbook is going to have a bold letter and most likely an arrow on top. They could just do it without the arrow as well. If you're talking about the magnitude, the way to note that would be with absolute value symbols, because the magnitude is just telling you the size of the vector. So you would use those absolute value symbols. All vectors will still have the same units. So for example, if it's a velocity vector, the magnitude would still have meters per second. So the magnitude, when you're looking at just the size of the vector, that's always going to be positive. When we write them, we use the vector notation, the arrow on top. I'll be honest with you though, there'll be times where we're doing velocity or acceleration, and I might not have all of those on there. I might get a little sloppy with that. And you'll see that later. Alright, so here's just an example. If you take displacement versus distance, the distance traveled cares about the path to get from point A to point B, whereas your vector is just going to be a straight line that connects those 2 points. That would be your displacement. Alright, another quick thing about vectors, doesn't matter where they are in space, if they have the same magnitude and the same direction, then they're going to be equal, which means, you'll see later, that we can actually pick up a vector and move it from one location to another location, and it still have the same exact value. But all of these have the same magnitude and the same direction in space. Two types of coordinate systems that we'll be using. One is Cartesian, which is just your regular X and Y system. And if you had a point P, you would say, oh, well, this is at the location 4, comma, 4. You could also use polar coordinates, and we'll look at that a little closer, where you would have the length from your origin to that point, and that would be representing the magnitude, but then you'd also have to give a direction. And we write that as r, comma, theta. Alright, so looking just specifically here, if you had your x and y coordinate system, if this point would be over 5, up 3. This would be over to the left 3, and negative 3, and up positive 4. If we had one down here, it would be negative and then negative. And if we had one here, it would be positive and then negative. So if we had this point in a Cartesian plane, we would say it's positive x, positive y. Or we could use this r. We could call it r, we could call it a, we could call it whatever. Typically in your notation when you're learning it, they use r. And then here is your angle theta. So it's still describing the same point in space. It's just one way we're saying, hey, go over here and up here. The other one is just saying, let's make a beeline and just go right to that point at a certain angle. Same spot in space, just two different ways to describe it. So what do we do with this? Let's bring in SOHCAHTOA and just remind you that the sine of an angle is going to be the opposite over the hypotenuse. Your cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. What does that mean for us in vectors? What that means is if we have this vector r, we could say, hey, let's describe it in terms of our components. So we have x and we have y. Well, how could we find the length of x or y? You would then say, okay, you know what? I need the length of this right triangle, and here's my angle theta, here's the length. So if I solved this guy for x, it would turn out to be x is equal to r cosine theta. And the same thing, y would be equal to r sine theta. So you could then just write in there that x is r cosine theta. And then y, it won't fit in here, but there we go. So here's another example. If you have the polar coordinates of a point, and you know that it's a length of 5.9 meters and an angle of 260 degrees, what are the Cartesian coordinates of this point? So what you would do is first let's get an idea, where is that? Okay, so if we drew this vector, you would say, starting from the positive x-axis, we know that that's about 260 degrees. And we know the length, well, 5.9 meters. And we know that this angle theta is 260. Well, what you want to do is you want to draw your, I'm going to use a different color. You want to draw your components to match up with the x-axis, positive or negative. So this would be my component in the x, and then this would be my component in the y. Okay, so the x component of this vector is going to be the vector itself, r, times the cosine of theta. But let's look at what our angle theta now is. This vector is located at 260 degrees, but we wrapped our components right around here, so we need this new angle. This new angle is going to be 260 minus this 180. So it would be 80 degrees. Then we would do Ry is going to be r sine theta, and that'll be 5.9 sine 80. If you take a minute and plug those into your calculator, you would know then that we would have our magnitude of our two components. And what you have to also look at is you have to realize, oh, well, you know what? This is a negative, and then this is also a negative. So both of these, when you look at the direction, you're going to have to put in that they're negative as well. So you can just put that in there. You can also go, if you know the Cartesian coordinates of this point, let's say this point is at 3, 4. It's really easy to go and get the magnitude of this r vector with the Pythagorean theorem, and then the inverse tangent to get this angle here. So let's use that as an example. If we had the point 3, 4, we could find the magnitude of r by saying the square root of 3 squared plus 4 squared. And we know that that's 5. And then the inverse tan of y over x, which is 4 over 3, tells me that that angle is 53 degrees. All right, so that's just going back and forth, and you'll have practice with that in your homework. Let me have you practice this one now. They're saying that the Cartesian coordinates are negative 3.5 and negative 2.5. So you went out, negative 3.5, and down negative 2.5. Find the polar coordinates of this point. So pause the video and try that out in your notes. And hopefully you came up with this for the magnitude of r, and this 35.5 degrees is saying that that is 35.5. But that's not really where r is located. What do you have to do to 35.5 in order to actually tell someone where that vector is located? You have to add 180 degrees to it. So we know that it's 216 degrees from the positive x-axis, which is normally where you measure angles from. All right, let's keep moving. Little things, little notes about vectors. When you're adding vectors or subtracting vectors, their directions must be taken into account. The units have to be the same. So you can't add a displacement and a velocity vector. You have to add ones with the same units. Graphical method. This is one way. I'm just going to show you how you do it. Typically, the only time you ever do that is when you're asked to do it. And then the algebraic methods are more convenient. But if you were to ask to add vectors graphically, you would use this head to tail method. So you would have your first vector, and if you want to add vector b to it, you would take the tail of it and put it at the head of vector a. You would also have to make sure that you're setting it up at the correct angle. From there, you will draw your connecting vector, which we call the resultant vector. That's why they're using R. And you would have to actually measure that, and you would need a ruler, and you would need a protractor. And you would also have to set your scale. So you might want to say like 1 centimeter is equal to 1 kilometer, for example. So you draw this out to scale, put the next vector up there, measure out the right angle that it's at, draw your resultant vector, measure that with a ruler, and use a protractor. You could do that with multiple vectors, and each time you would have to get your protractor, get your ruler, measure these angles correctly, go here, measure this guy, go here. You can see that it's pretty cumbersome, and then you would draw your resultant vector. But you always put them head to tail. So we typically, when adding vectors, all your vectors must have the same units. We already said that. Same type of quantity, we said that as well. Let's look here. One other good thing to know is there's always going to be a vector that you can add to yours in order to make the resultant 0. And all that is if you have a positive A, there exists a negative A that's the same magnitude, just the opposite direction. And the reason we say that is because that'll lead us into this idea of subtraction. So you can have vector subtraction as well. If you had vector A, and then you had vector B, if you were to add it, you would do head to tail. If you're subtracting it, instead of drawing it this way, you would flip it 180 degrees, and you would still do head to tail, but now the resultant vector is this way. And that's what this vector C, this resultant vector in this example, is going to be vector A minus vector B. All right, a couple of other quick notes. If you multiply or divide by a scalar, you still keep your vector. And that'll make more sense as we do more complex math a little bit later. But let me say the magnitude of the vector is multiplied or divided by a scalar, you'll still get your vector. So, for example, if you had vector A and you multiplied it by 2, your result would just be 2A. It would be, like if this is vector A, that would just be 2 times as long. Same direction, everything else stays the same. If you multiply vector A by a positive 2, then your result is going to be positive 2A, still vectors. If you multiply it by a negative 2, then your result will be a negative 2. Alright, so this graphical method, you don't want to use it if you need accuracy. You don't want to use it if you have a three-dimensional problem. You want to use your component method, which we're going to go over next. So in other words, you only use the graphical method if you're asked to do so. Before we go into that, let's get into this idea of what a unit vector is. A unit vector has a magnitude of 1 and a direction. We're going to use this notation. So we have I, unit vector I is in the positive x direction. And it's got this little caret on top, and we actually call that I hat. So they call it a little hat. The j unit vector is in the positive y direction, and the k is in the positive z direction if we have 3 dimensions. The magnitude of each one of them is 1. So ultimately, why we use it is just to specify the direction of your components. There's no like real physical significance to it. So let's see what that means. Here we go. We have vector A. Here is my x component, and you might see your y component drawn over here. I'll show you in the next slide, but I don't like it this way. I like to complete the right triangle, and you're allowed to do that. But let's just use this slide for a second. So here is your component in the x direction and your component in the y direction. You can use these hats to describe your vector A. So this is just what the notation is going to look like. So like I said before, you can draw your components this way. I don't like to do that. I like to go left or right and then up or down. If you go left or right and then up or down, you can just remember that these are always true. Your x component will be the magnitude of the vector times the cosine of the angle, and then the magnitude of the y component would be the magnitude of the vector times the cosine. However, that's assuming one really important piece of information. That's assuming that you are around that x-axis. Like I said, you go out left or right and then up or down. You could have a problem though that says this, where theta is, say, 40 degrees east of north. Well, if you do that, you have two options. You can either take it as it is, and you can say, here's my x, and here's my y. Or, what I typically like to do is if they give me this, and this is 40 degrees, then I know what this is. This is then 50 degrees. That allows me to go back and go out and then up. And I know that this is 50 degrees. So it's up to you. If you end up doing it like so, and you go, actually you go up and over. If you do it that way, just remember that your components don't follow this rule. Your components would then be switched. And you can do that just by looking at the right triangle and your third function. All right, so you have two, and you'll get comfortable doing this the more you do. So here is our unit vector notation. We could call vector A at a certain angle, or we could say it is AX in the I direction plus AY in the J direction. And if you get used to that, it's really a great idea because you'll see how easy the math gets. But really just think about those components as the legs of the right triangle. And if you wanted the magnitude, you could just use the Pythagorean theorem, and then you could find your angle using the inverse tangent. Alright, real quick, your components for your vectors are either going to be positive or negative. You have to be really careful with that. If your vector's in this first quadrant, then you have positive x, positive y. If it's over here, it's a negative x and a positive y, and so on and so forth. If it's down here, we know that's negative, negative. If it's down here, that's positive, negative. So just be real careful when we're practicing those. So let's do an example with a position vector. Here's the spot. We want to know where that spot is located. We have vector r. You could look at it, you might be given your component here to describe vector r. And that's really all a component is. It's just the legs of that right triangle to get you to the same point in space. Now let's look at this. Consider these two vectors. Let's see if you can draw them. Pause the video real quick. Draw the coordinates and see if you can figure out where these vectors are located. Well, here's my 2i and my negative 2j. The vector A must be right here. And same thing over here. We have negative 1i, negative 5j. So my vector B has got to be right there. You can find the length of vector A and vector B, and you can find the angle. You have everything right here, so you could say, you know what? The magnitude of vector A is going to be 2 squared plus 2 squared square rooted. The magnitude of B is equal to square root of negative 1 squared plus negative 5 squared. Let's do that calculation real quick. And so those in. You could find the angle. You can find this angle. And you would just use right? Is the inverse tangent of negative 2 over 2. and then you would just describe however many degrees that is, and you could say it's south of the positive x, or below the negative x, below the positive x, or south of east, all different ways. When you get this angle, remember you have to include that extra 180. Okay, so here is the practice in vector addition and subtraction. And when you have them in component forms in our unit vector notation, it makes life so easy. So I'm going to run through and then I'm going to let you guys practice. If you calculate vector A plus vector B, you just have to add the components. So it's real easy if you write them over top of each other. And go ahead and pause that and see what you come up with. So you get 2 plus negative 1, so that's 1i, and then negative 2 plus negative 5 is minus 7j. Now that's a plus b. You could do a minus b. Same idea. 2 minus negative 1, which gives you 3i. Negative 2 minus negative 5, which gives you a positive 3 in the j direction. Now, these are asking for the magnitudes of each of these. Remember, the magnitude is just going to use the Pythagorean theorem. And then the direction of these. And the theta is going to be using the inverse tangent. So pause the video and try to get those, and I'll put the answers up. Okay, so hopefully you got these answers for the magnitude. I just used the Pythagorean theorem using these components up here. And then our angle. Well, if you think back to where we drew this vector, if it has negative 1, negative 7, our resultant right here is going to be all the way down like that. So that negative 82 is saying from the negative x-axis. So that's one way to put it. The other way is to describe it as from the positive x-axis. So you would just take that 82 and add 180 to it. And then a minus b, that one's an easy one. When you draw that, you have your components like this, and then that's your angle theta. You could have vectors in 3 dimensions, and it's really just no big deal. Like here's our I that we're used to, that's our x direction, our y direction, and that's our third dimension, our z direction. You treat it all the same. Add up all of your i's, add up all of your z's, add up all of your k's, and then you do with this resultant vector. And you'll have practice with that in your homework. You could find the magnitude of that resultant. You can expand your Pythagorean theorem into 3 dimensions. And then you would have your angles for this each direction separately. So you could find your x direction. You could find your y direction by using the magnitude, etc., etc. You could also add multiple vectors. You could have 7 vectors if you wanted and add them up. You're still going to go through the same thing. Add up all of your x's or all of your I directions for each one of those vectors. Add up all of the ones in the j direction and all of the components in the k direction. All right, so here is our final slide. We're going to actually go through one of these examples, and there are a couple ways we can do it. I think what I'm going to do is I'm going to do it in the unit vector notation, and then in class or on another video we'll do it kind of old school style, and then you get to choose because you can approach the problem in multiple ways. So we have a hiker. She begins a trip by first walking 25 kilometers southeast from her car. She stops and sets up her tent, and on the second day she walks 40 kilometers in a direction 60 degrees north of east. And at what point she discovers the Four Springs Tower. She wants to know where is that tower in relation to her starting point. Always a good idea to start out with a diagram. Here we go. So, 25 kilometers southeast. Well, that assumes that that's just 45 degrees. Southeast, this way is east, north, west, south. So 25 kilometers. Then at what point she then travels the next day, she's 45, so this would be 60, and it's longer. So we know that this is 40 kilometers. What you want to do is find the resultant vector from her starting point out to this tower. So we'll call it the resultant. Alright, so what do we want to do? Well, we could say that this is vector A and this is vector B. And we could write it in unit vector form, right? So let's look here and we could find our components for this vector. There's my x, there's my y, so ax, ay. We could also then do it for this vector. And we could go, oh, I really should do it in another color. Here's my dx, and then my dy. How do I find this component? Well, this is 60. This is 45. Use your trig functions, and you will end up, if you have your angles right around the x-axis, you're good. You can say, well, vector A is going to be the magnitude of vector A, which is 25, cosine 45. That is in the I hat direction. And then for that, we go down. So that's going to be a negative 25 sine 45. And that's in the J hat direction. Now pause the video and you try to write vector B. And see how I write without my vector symbol. Hopefully you came up with that. So let's get some working numbers in there for us. 25 cosine 45 turns out to be 17.68. That's in the I direction. And this would be negative 17.68 in the J direction. So you don't have to keep the plus and the minus there. You can just write it right. That. So that's vector A. So what does that mean? It means that if I were to go over 17.68 and then down 17.68, I would find this location. I would find her camp. And then, if I were to go over and up, I would find that tower. And what does vector do? This number punches down to 20 I hat plus 34.6 j hat. Your resultant vector, the distance from her starting point to that tower, first you're going to have to add up all of your i's and all of your j's. So let's first look at this, and we'll say, you know what, that's going to be 37.68 in I, and then you take 34 and 17, will be a positive 16.92 in the J. So that's great. That'll tell me if I go over 37.68 and up 16.92, that'll give me where this resultant vector is. But I want to know the length of it. So to find the length, the magnitude, we're going to use the Pythagorean theorem. So you go ahead, try that. And I got 41.3 kilometers. And then I can figure out the angle that it makes with the x-axis, and we know that we're going to use the inverse tan of 16.92 is 37.68. And I got an angle of 24.2 degrees. Alright, so you try it, check it out, and then the next time you see a video, I'll do it a different approach. Alright, thanks for hanging in there.